Curvilinear coordinate systems 23. Now we're dealing the second part of the problem. Derive the curvilinear curl considering the possible variation of the scale factors along each surface of the volume. In the first video, we talked about the divergence. Now, as for the curl, we can use the integral definition. Curl A dot limit as s goes to 0. The surface integral of d sigma is the limit as the contour C goes to 0, closed contour integral dr dot A. So we're looking at the differential limits. So C is a closed path surrounding the surface S, and d sigma direction is determined by the right-hand rule applied to the path C. Okay, so if we're doing this on this contour, you can see that if we're going in the counterclockwise direction, this is Q1 hat, Q2 hat, and Q3 hat. Now, this is the closed path surrounding the surface. So for this surface, we would have, instead of x and y, dq1 h1, so because we're going only in this direction, dq2h2 and dq3h3. We don't have any dimensions along the one-axis. So it's h2 dq2 instead of y and h3 dq3 instead of z, but it's in q1 hat direction, and if it's in q1 hat direction, the right-hand rule tells us that we should be flowing in the counterclockwise direction. So limit as s goes to 0, d sigma, integral of d sigma. So this is going to be h2 dq2, h3 dq3 in q1 hat direction. We're taking the dot product with curl A, which means we're looking at the first component of curl A. So we're looking at one component of curl A. Looking at the right-hand side of this equation, we have to evaluate this A dot dr along this path. So that means if I go over CA and CC sections, I would be dealing with, because I'm moving on the two axes, h2 dq2, which is going to be my dr on that axis, multiplied with the second component of A2. So this is basically A2 vector, the second component of A. Vector field A. And if I'm moving on B and D axes, then I would have an integral over CB and CD. Now I would be dealing with H3 dQ3 because I'm moving on the third axis, and I'm also, because it's a dot product, I'm dealing with A3 component. Okay, now as for the differential displacements along CA and CC, I would have H2 dQ2 in Q2 hat, and as for B and D, I would have H3 dQ3 in Q3 hat. But when I take the dot product with vector A and perform this integral along a certain direction, these vectors will change sign. For example, if I'm looking at CA, now because I'm moving in the counterclockwise direction, this time I have H2 dQ2 Q2 hat dot product with A2, and A2 vector is A2 Q2 hat. So this would give me H2 A2 dQ2, and we're at the bottom here. So we have Q1 Q2 Q3. This has to be evaluated at Q1 Q2 Q3. Okay, if we move to the top, now we have moved from Q3 to Q3 plus dQ3. We would have the same thing, H2 A2 dQ2, evaluated at Q1 Q2, now at Q3 plus dQ3. But because we're moving in minus Q2 hat direction, this would have a minus sign. A2 Q2 hat dot product with minus H2 dQ2 Q2 hat. So there's going to be a plus or minus here, which is determined by the direction. Okay, so this is in minus direction, so we would have this. Now it's evaluated at Q3 plus dQ3 instead of Q3, because we moved up. So H2, A2 evaluated at Q1, Q2, and Q3 plus dQ3, I can use Taylor series expansion. dQ3 equals to 0 gives me the first non-zero term. And then I take a derivative of H2, A2 with respect to Q3 multiplied by dQ3. That gives me the first order term in Taylor series expansion. So if I add these two, you see now for the CC integral I have a minus sign. So this is going to be multiplied by minus dQ2. So it's multiplied by minus dQ2, and this is plus dQ2, so they would cancel, but I would be left with this term multiplied by minus dQ2. So this is what I have, minus dQ2 dQ3, partial derivative H2 A2 with respect to Q3. Now, if I were to do it for the contours B and D, this time I would have the H3 dQ3 in Q3 hat. If I'm moving along CB, it's plus. If I'm moving along CD, then it's going to be minus. So for CB, it's H3 A3 dQ3. And for CD, it's minus H3 A3 dQ3 evaluated at Q1, Q2, Q3. So along CB, I'm at Q2 plus dQ2 because I moved on the two axes. And here it is at Q2. So doing the same thing here for H3, A3, approximately at Q2 plus dQ2 is given by this Taylor series expansion. Adding them up for when I multiply this by dQ3 and add up the contribution from the other contour, which is the CD contour, I would have these terms cancelling, and this will be remaining multiplied by dQ3. So the SC goes to 0, integral A dot dr for CB plus CD gives me this contribution. Now, if I add these two contributions, I would have the limit SC goes to 0, close contour integral A dot dr is H3, A3 partial derivative with respect to Q2. And here I have minus H2, A2 partial derivative with respect to Q3 multiplied by dQ2, dQ3. So that's the right-hand side of the equation. The left-hand side gave me dQ1, dQ2, dQ3, H2, H3, and curl A's first component. So curl A's first component is then 1 over H2, H3. These dQ2, dQ3s will cancel. Partial derivative H3, A3 with respect to Q2 minus partial derivative H2, A2 with respect to Q3. I can repeat this for the second and the third, and basically I obtain similar expressions from these surfaces, and this is the end result I get. This set of equations can be summarized as 1 over H1, H2, H3 determinant of H1, Q1 hat, H2, Q2 hat, H3, Q3 hat, partial derivatives Q1, Q2, Q3, H1, A1, H2, A2, H3, A3. And in subscript summation notation, this can be written as epsilon ijk 1 over hj hk partial derivative with respect to qj of hk ak in qi hat direction. So there are two ways to show this. Okay, so basically using the this integral definition of the curl, we were able to reproduce the curvilinear expressions for the curl operation.